Hello everyone. So this is lecture 2 in week 10. So recall from the previous 6 lectures, that is all of week 9 and the first lecture in week 10, that we have actually discussed the simplex method in detail, right. So yeah, that's actually an age old method, you can say, for computing the solution in for an LP problem, right. So a linear programming problem. So yeah, you can recall the name Danzig, right. So formulated this algorithm, the simplex algorithm, in the 1940s, right. So it's 80 plus years since he formulated the algorithm, right. And if you recall, we mentioned 2 issues of the simplex method, right. Yeah, so one is that finding a BFS initially could be a hard task. Okay, so yeah, people did improve this part to some extent a little later. I mean, after Danzig, right, on how to find a BFS initially. Right. So, I mean, we are not going to discuss that since we have other algorithms to discuss. Yeah, but the second issue is it is not solvable. Okay. So, it is actually a problem with simplex method that in the worst case, okay, yeah, it could end up kind of traversing all the vertices and imagine, for example, if n is 50 or n is 100, right. So, and you had this particular problem, this exact problem what I had given at the end of the previous lecture, right. So, it will actually take 2 power 100 iterations. 2 power 100 is 1 followed by 30 zeros, right. So, that is it's just huge, right. So, that is an inherent part of simplex algorithm, nothing can be done. Okay. So, maybe the right question to ask is, if simplex method has this issue, in the worst case that it could take so many iterations, it may end up traveling all possible vertices, right. So, why did people use simplex method at all? Because in the worst case it can be as bad as brute force, right. So, why did people use simplex method at all? The reason is, other than a few pathological examples like this. So, one of the examples that I gave in the last class was a pathological example. Okay. So, yeah, there are a few pathological examples like that, but in general, so you take up a linear programming problem, simplex method gives the answer in a very few steps. Okay. Of course, there are certain pathological examples, but in most of the cases the number of steps that a simplex algorithm takes is actually very few. Okay. So, it is just this pathological example that has derailed our discussion. Okay. But in general, that is not the case. For most of the examples that you considered, you will see that simplex methods gives the answer in a very few steps. There were a few other methods, like for example ellipsoid method. Okay. So, maybe you can look at these methods if you want. Okay. So, other methods or other algorithms, let me call it, to find a solution to LP, right. So, you can, I mean, there are a few other algorithms at least, and this is one method that you would find often when you search for algorithms to solve LP. Okay. Ellipsoid method actually does not have this issue, that yeah, in the worst case it is I mean, it does not take so many vertices. I mean, it solves in say in polynomial steps in n, say n squared or n cube or something of that sort. Okay. But that is the worst case guarantee. But in general, if you actually give some linear programming problem to simplex algorithm and some linear programming algorithm to ellipsoid method, you will see that simplex method in most of the cases or you can see in almost all the cases except for these pathological cases, simplex method outperforms ellipsoid method. Okay. Though ellipsoid method has what you call as the worst case guarantee, okay, people were still using simplex method because in practice simplex method gave the answer in a very few. So, that is one of the reasons why I am not teaching ellipsoid method, because ellipsoid method is completely outdated. You can kind of say simplex method is also outdated, but at least for academic purposes people teach simplex method. The reason is yeah, it was I mean it gives a very nice perspective of linear programming problems. It gives you so many properties of linear programming problems, right. So, yeah, simplex method is still used in the literature, but in practice people have moved to more sophisticated methods, right. So, and yeah, some of those are like there is something called as the affine scaling method. Okay. And you also have Karmaker's algorithm. Okay. So, yeah, so I told you that in 1940s Danzig came up with the simplex method. So, the next most useful method that was set to replace the simplex method, right, was the Karmaker's algorithm. Okay. So, it is popularly called as the interior point method. Actually both affine scaling and Karmaker's algorithm are called as interior point methods. Okay. So, the reason is, if you recall how we find the solution in simplex method, right. So, we start with a vertex, keep moving around different vertices until we converge to the answer, converge to the solution, right. So, you can actually call simplex method as an exterior point method, because or rather the boundary point method. Exterior point is not the right term, I am sorry, the boundary point method, because it only traverses the boundary, right, it never goes inside the feasible set, right. So, for example, if you have a feasible set of this form, okay, I am just drawing it as my hand pleases. Okay. So, yeah, this is let us say the feasible set in 2 dimensions, yeah, that is when I can draw, right. So, what does simplex method do? Simplex method starts with this point, then it traverses here, then it traverses here, then it traverses here, I mean as an example, then it traverses here, right. So, what simplex method does is it traverses the boundary points, in fact vertices to be even more precise, but yeah, nevertheless it travels on the boundary, it never goes to the interior. You will never see simplex method, the iterates of simplex method going like this. Okay. Suppose this is the answer, as an example. Okay. You will never see, let me draw it in a different color, yeah, you will never see it going like this if this is the answer, right. So, let us say this is the solution and this is the starting point, right. So, simplex method always traverses like this, or yeah, maybe like this, but never in the interior, right. So, simplex method you can call it as a boundary point method. Okay. Whereas, the affine scaling method and Karmaker's algorithm travels using the interior. Okay. So, yeah, you can also start from an interior point. Okay. So, recall that yeah, simplex method starts with a vertex and moves across the vertex. So, in affine scaling method or Karmaker's algorithm, right, you can start at an interior point, you need not start at a vertex, you can start at a vertex also, but you can also start at an interior point. Okay. And how does the iterates traverse in the feasible set? It actually traverses in the interior of the feasible set. It does not traverse the boundary points as the simplex method did. Okay? And so this is what am I basically saying? I am saying that this is actually a very different method. Of course, both Karmaker's algorithm, affine scaling method and simplex method, they are all solving the same LP problem, right, but the way it approaches a linear programming problem is very different. So the simplex method approaches by traversing the vertices. Karmaker's algorithm and affine scaling method approaches by traveling in the interior. So you will actually see no connection between the algorithm what we saw for simplex method and what we are going to see for the interior point methods now. Okay. So keep that in mind. This might be new to you because yeah, if you recall how we did build up the algorithms for unconstrained optimization, how did we do that? We started with gradient descent, we improved it to conjugate gradient, then with a slight variation we moved to Newton's method and we improved it to quasi-Newton method, right. So all the algorithms were related. Similarly, when we did for constrained optimization, we started with quadratic penalty method, we improvised it to augmented Lagrangian method, right, but that is not the case here. Okay. We started for linear programming problem, we started with simplex method. We are going to now discuss some interior point methods which actually has absolutely no relation with simplex method. Okay. So yeah, that is something to keep in mind. And for yeah, so I was saying about the trivias, right. So in 1940s Danzig gave this simplex method until Karmaker, who is actually a graduate of IIT, he did his BTech at IIT Bombay. So he designed this algorithm called Karmaker's algorithm, which is actually which actually performs better than the simplex algorithm, okay, and it also gives a polynomial guarantee. So it does not take 2 power n steps and all that, okay. So yeah, it takes very less number of steps. It removes the pathologies or the issues that are found in simplex method. So but yeah, people had to wait for like 40 years to actually have this improvement. In fact, I mean the reason is this, I mean people were trying to work around the simplex method in some sense. So Karmaker's algorithm is something out of the blue, I mean it approaches the problem in a very different way, okay. Alright, so yeah, with this amount of trivia we will actually move to these methods, okay. So yeah, we will work with both affine scaling method and Karmaker's algorithm, okay. We will start with affine scaling method, okay. So the good part, though I said that the simplex method and affine scaling method, I mean are very different, okay. The first step actually is common, okay. So you have to start by converting the given LP to its standard form, okay. No escape from that. So it has to be converted to this form. You minimize C transpose x subject to Ax equal to B, x greater than or equal to 0, and the rank of A is equal to the number of rows in M, okay. All right. So yeah, maybe I will write that too, rank of A M cross n is equal to M, okay. So that is anyway the first step, no respite to that. We will actually first learn the idea and then I mean go ahead to frame the algorithm as such. Okay. So, the idea is you can say similar to what we did in gradient descent. Okay. So, what did we do in gradient descent? We when you are given an initial point, you have to find a descent direction, and the descent direction is just the negative of the gradient of the objective function, right. So, the gradient of the objective function is just C here. So, you can see that the objective function is C transpose x and the gradient is C. So, the negative of the gradient is minus C. Okay. So, great. So, are we just saying that the descent direction at each step is minus C? Wait a minute. Okay. So, yeah, if it was that easy, I mean it would not have taken so long, right. So, we need to I mean if you just blindly choose minus C, okay, you can actually end up going out of the feasible set, right. So, for example, if suppose you start at this point and minus C is in this direction, okay. So, you might actually end up going out of the feasible set, right. So, that is not, it does not stop with choosing the steepest descent direction, that is the negative gradient. Okay. You have to project minus C, right, that the steepest descent direction onto the null space of A. Okay. So, you should ask why, I mean what is so great about the null space of A. So, I suppose you are familiar with what is null space. Null space is the set of vectors, null space of A is the set of vectors x for which A x is equal to 0. Okay. So, yeah, I mean, so null space of a matrix A is, yeah, so I will denote that as null of A. So, that is the set of all x for which A x is equal to 0. Okay. So, as simple as that. Okay. So, what I am claiming is that you have to project the vector minus C is a vector, right. You have to project that onto the null space of A. So, why null space of A after all? So, note that we actually want each point xk, right. So, x1 x0 x1 x2 dot dot x yeah, wherever it ends. For all that x we need it to satisfy Ax equal to b, right. So, that is we want Axk equal to b and Axk plus 1 equal to b, right. Of course, for any k, that is that must be true, right. So, if xk plus 1 is xk plus alpha dk, okay. So, this is what we do usually, right. So, you start with alpha k dk maybe if you want, okay, but yeah, anyway it is a scalar. So, what that means is that xk minus xk plus 1 minus xk is alpha k dk, right. So, A into yeah, I will write as A dk, okay. A dk is A into xk plus 1 minus xk by alpha, okay. So, yeah, this is 1 by alpha into Ax plus 1 minus Axk, okay. I am just multiplied this. So, Axk plus 1 minus Axk, but both of them are b, right. So, that is 0, okay. So, I can actually retain the point within the feasible set, okay, if my direction dk is such that A dk is equal to 0, right. So, yeah, let us say you have found an x0 such that Ax0 is equal to b, that is a feasible point, okay. I want to move to x1, but I want to ensure that Ax1 is also equal to B. How do I do that? Very simple, I choose D such that AD is equal to 0, okay, which means I have to choose a D that is in the null space of A. Okay. So, great. So, I will choose something in the null space of A, but it also has to be a descent direction. Okay. So, what I am going to do is to project the known descent direction. I know that minus C is certainly a descent direction, okay, but I do not know if it is I mean if it belongs to the null space. Yeah, it usually does not belong to the null space. So, what I am going to do is to project minus C onto the null space of A. Okay. So, the idea is to project minus C onto onto null of A. I will just write. Okay. Great. So, that is the idea, fine, but how do we project, right. So, that is case you have learnt projection in linear algebra, I mean this should be very straightforward, but yeah, since even those who have learnt linear algebra sometimes I mean are not very well versed with projections, right. So, let me spend about 5 minutes discussing what is the projection of minus C onto the null space of A. In fact, I will derive that mathematically. Okay. So, before that you should be knowing that the null space and the row space of a matrix are orthogonal to each other. That is, if you take a vector from the null space of a matrix and you take a vector from the row space of a matrix, they both are orthogonal, right. So, any vector can be split into its orthogonal components, right. So, yeah, I mean if all this is Greek and Latin to you, understand it this way. So, consider x axis and y axis or x1 axis and x2 axis, right. So, if I give you a point, you can certainly split it up into a component in x1 axis and a component in x2 axis, right. So, I give the point 4 comma 5. So, you will immediately say that 4 is the component of x1 and 5 is the component of x2, right. So, I will write that as 4 comma 0 plus 0 comma 5, right. It is not just for x1 axis and x2 axis, but for any two orthogonal axis. Say you can take the 45-degree axis and 135-degree axis, just to give you an example. You can split 4 comma 5 or any given point into a point in the 45-degree axis and a point in 135-degree axis. You can do that in n dimensions. Okay. Now, since the row space and the null space of any matrix are orthogonal, right. So, I can split a given vector to be the sum of two vectors, where one of the vectors is in the null space and one of the vectors is in the row space, okay, of the matrix. So, if I do that, so let me do that for C, I mean we will change that for minus C at the end. So, let me call that CR and CN, okay, where CR belongs to the row space of A and Cn belongs to the null space of A. Okay. So, yeah, row space of A is all vectors that can be written as linear combinations of the rows of. Okay. So, yeah, so suppose you write C equal to CR plus Cn. Okay. So, in that case you will have, so since Cn belongs to the null space of A, it implies that ACn equal to 0 and CR belonging to the row space of A means that A transpose lambda is equal to CR. Okay. So, that is CR can be written as or CR transpose can be written as lambda transpose A, right. So, this is so if lambda is like the linear combination, say lambda 1 lambda 2 dot lambda m. Okay. So, lambda 1 scales the first row plus lambda 2 times the second row plus dot 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 lambda m times the nth row, mth row, sorry, right. So, that is CR, right. So, you can actually write CR as CR transpose as lambda transpose A or CR as A transpose lambda, okay. I am taking the transpose on both sides, okay. So, that is CR, okay. Now, the question is, can I find lambda, okay. Of course, I can. So, to find lambda, I will actually write ACR equal to ACR equal to AA transpose lambda, okay. And I claim that AA transpose is invertible. Why is that? Because the rank of matrix A is equal to M, right. So, AA transpose will be an M cross M matrix, and yeah. So, since it is the product of two rank M matrices, right. So, you will get rank M matrix as well, right. So, an M cross M matrix having rank M is non-singular. So, you can invert AA transpose. So, pre-multiplying AA transpose on both sides, you will have A transpose inverse ACR equals lambda, okay. Okay. Now, okay, so yeah, what we actually need is Cn and not lambda, okay, but we will use this to find Cn. So, note that C equals Cr plus Cn. So, that implies Cn is C minus Cr, right, but what is Cr? Yeah, so if I substitute this quantity A transpose inverse A here, right. So, that is I am just substituting the value of lambda here. So, you will actually get okay. Now, so yeah, before this, so yeah, let me actually find what is, so this quantity now, what is A transpose into A transpose inverse A into C, okay. So, that will be, so instead of C I can, C is actually Cn plus Cr, recall that. So, you have A transpose inverse A into Cn plus Cr, okay. So, that is A transpose inverse A into Cn, but A into Cn is 0. So, all of this is 0, okay, because A Cn is 0, and the remaining is A transpose inverse A into Cr, okay. Note that this is lambda, right. So, A transpose inverse A Cr is lambda, right. So, this actually the whole thing actually turns out to be A transpose lambda, but A transpose lambda is actually Cr, okay. So, I can pre-multiply with some complicated matrix equations A transpose inverse A into C, so that I actually get the projection of C onto the row space of A, okay. So, to get the null space, right. So, Cn is just C minus Cr, right. So, because C equal to Cr plus Cn, so Cn is C minus Cr. So, this is just I minus A transpose inverse A into C, okay. So, IC is C, and yeah, A transpose inverse AC is Cr. So, this is what is Cn, okay. So, when you want to project a vector onto the null space of a matrix, okay. So, you just pre-multiply the matrix with I minus A transpose inverse A, okay. So, yeah, that actually gives you yeah. So, so you can say the projection of C onto null of A is I minus A transpose inverse A into C, okay. So, what is projection of minus C? very simple, I just have to replace C by minus C. So, you will have minus of I minus A transpose inverse A into C. Okay. So, what we have done until now is, so when you are given some x 0, okay, you want to choose a particular direction in such a way that it is a descent direction, as well as you will stay within the feasible set, right. So, what you should do, very simple, choose the direction in such a way that it is the projection of minus C onto the null space of A, that is you need to choose minus I into minus of I minus A transpose inverse A into, okay. Fine, we will continue the algorithm in the next lecture. Thank you.